Hello and welcome back to Compiler Programming. Today I'm gonna start working on the register allocation. I have no idea how much we will be able to have done today, but it's definitely time to get started. And the first thing before we can do any actual allocation is that we need to be able to track the state of the registers across function boundaries and more precisely even code block boundaries. So as far as code block goes, this is just anything between curly braces, right? So you have stuff like this, right? It has its own scope. And since things can go out of scope at the end of the curly brace, that would also mean that if we did any register allocation or if we did anything funky during this part, then it would be necessary for us to do the same sort of tracking of registers as we would do for the function itself. For that purpose, I did a small refactoring in between the episodes where I just extracted the instructions that go inside the functions into a code block. I don't know if that's necessarily the right way to go about that, but this is what we're gonna stick with for now. And additionally, we need to be able to know the state of the register. And this is where it gets a bit tricky, especially I think some terminology is better than other terminology, but let's start with that. So we have register state, and we have many of them. So first of all, we have sort of non-volatile, and we have volatile. So this is the terminology that you would hear a lot about registers, and I honestly think it's not that great. There is other version of this which might be better to use. So it's a bit weird, right? There is widespread, not so good terminology, and there is less it's proliferated better terminology, at least as far as I think. And choosing between them is a bit tricky because in one case you will not have something that's commonly used, in another case it may be slightly better. I don't know. Anyway, so we have non-volatile and volatile registers. So what is the difference between them? And the other terminology should actually clear this up. And volatile registers are registers that are saved by the caller. So they are otherwise called caller saved. And non-volatile are callee saved. So what does it actually mean? And let me close out the camera. Okay, what does it actually mean? That means that if we have a volatile register, then like if inside of a function I'm using a volatile register, that means it's my responsibility to save that register before calling any other function. And non-volatile is sort of the opposite. So when my function is called, so let's say like this function is called, right? And I will allocate a bunch of registers for all these variables, and I will not have enough volatile registers to do that. Then at the end of the function, I will have to restore the value that register was before the function started. You also might have noticed that this was mentioned when we were dealing with exceptions, and that means that we will also have to change this particular implementation as well once this is done. So there is this UOP push non-volatile, and this is exactly what it describes, right? So we will be saving a non-volatile register at the start of the function in the prologue, and then we will be restoring that in the epilogue. So I think I will continue using this terminology because it's a bit more common, but this comment might be okay. And I don't know which one should actually be the default value of this enum, but probably doesn't really matter. But another thing that we need to track is that whether this register is actually available right now, or is it not available right now? And there are a couple of ways we can go about doing it. So we can have so we have a bit field for availability of the register, or we can just put all this stuff into the same enum. So we'll have a combination where we have non-volatile occupied and non-volatile occupied, and other way around. Honestly, probably I want them separated. I don't exactly know if that would be the right way to go about that. Let's think about it. So what it would look like if we just use bit fields for this stuff. Okay, then I guess we will not need to have any extra definitions for these things, and we will just need to track it. Okay, so let's go to code block, right? And let's start tracking this. So we have 16 registers, general purpose registers, but we also have XMM registers. We also have e-flags, and it might be that we will need to end up tracking other things. So let's just put the whole U64 as register state. So we say volatile register bitmap. So if something is 1 in this bitmap, then it is volatile. If it's 0, it's non-volatile. And here we will say, maybe I'll do it a bit differently, register volatile bitmap, and then register occupied bitmap. Okay, so that looks good. They will both be initialized to 0 when we create a code block, and right now that happens only on the creation of the function builder, so I'm not tracking registers as said between the curly braces for regular code blocks, but that's something we can do later on. For now, we can just start here. And the initial state of this stuff will actually depend on the calling convention of the code, because this is what prescribes for the function, at least, what are considered volatile registers and what are considered non-volatile registers. This is why I have this calling convention here, and this is where it would say somewhere volatile. Okay, so we have basically the argument registers and register like array-x, R10, R11, XMM4, and XMM5 are considered volatile. So there is this other terminology as well as color Kali saved registers. Let's look at what it points to. Okay, it's basically the same thing as the other one. So yeah, cool. I'm not going to go into YMM, ZMM registers, like all of this AVX stuff, First of all, as far as AVX512 goes, nobody really has it. So that's basically unimportant, at least at the time of the recording, because it's more like a server CPU thing. Eventually, we will definitely need to support it, but right now it's not important. YOM, which is, I believe, AVX2, they are more widespread, so that's something that needs to be supported, but not right now. And XMM we sort of already have, but right now it might be, we might need to do extra work to support them. So for today, I'm just going to focus again on the integer registers and deal with those. If they work, it should be relatively straightforward to support XMM stuff. Okay, so we have function begin, probably, no? Yeah, it's in here, yeah. Okay, so this is where we create the code block, and now we will need to set up our registers correctly. So the question is, do I want to create a wrapper type to tell that this is actually a bit field? Maybe I do, maybe I don't. I don't know. For now, let's continue like this. So we'll say void register set volatile. It will accept a pointer to the bit field, and so bitmap, and then it will accept. Actually, don't like bitmap because it's a bit ambiguous. Let's call it bit array, bit field, bit set. Let's call it bit set. Okay, and we have a register or better operand, actually, because XML registers will be slightly different, and then you have a flags, which is not really a register, so I think this is much better. Let's mark it as inline, and let's figure out what we need to do. Well, for the regular integer registers, it should be pretty straightforward. All we need to do is take the bit set and add to it one LLU that is shifted by operand reg, I guess. So, and here we should assert that operand, or let's do it this way, if operand type is operand type register, and we do this device, we will panic and say that is to do. Okay, that looks reasonable. Does it build? It does. And now we will need to actually set a bunch of registers. So let's do it like that. Create a block and say register set volatile builder code block register volatile bit set. And do I want operand or do I not want operand? Okay, I think I have operand, and I'm not going to track sort of AH versus AL. So I'm not gonna track the halves of the registers because that's just gonna be a bit of a madness. And the only situation where we're really using it is inside of integer division, and I don't think that's gonna be anywhere else. So for now, I'm just gonna assume that we don't care about the size of the register. You occupy the register fully instead of being able to address its parts. So I'm gonna say we want volatile ones, right? So that's gonna be R10. Okay, this needs to be dot, and this needs to be R10. And we have some problem with const qualifiers. I guess that's because this is const. Okay, that sounds fine. So we can do that. We can add more of them. And let's see. So these are arguments. So we have RCX, we have RDX, we have R8 and R9. Then we have our return, and return is REX. And we have other, which is R10 and R11, right? So let's verify. REX, RCX, RDX, R8, R9, R10, R11. And then there is XMM stuff, but I said for now we are just ignoring the XMM stuff. As far as occupy things go, this is where we will need to track it when we assign arguments to the function, right? So first of all, let's try to run this and make sure that this does not actually break anything. This seems to be fine, at least for now, because we are not using it anywhere, but you never know. Okay, and what else? Well, we also want to have another one that is set occupied, and it will be read set and operand. That sounds good. Now that I see that they are exactly the same. So I'm actually gonna put them into one, and I will say register bit set set bit or set. Okay, and we will need to have a similar function that is for getting, and basically we will say I will get it by value. That will actually be easier, and say return, so not of bit set and this. I'm never sure about the precedence of bitwise and an or, so rather be safe. And this is necessary because I want to the bit can be at any position, and I want to force it to be at either at the first position. So the value will be 0 or 1 and not 0 or something else. Okay, this is now bool, and I think actually it's probably better suited to be here. somewhere. Where's our operand stuff? Okay, here's probably a good place to put these. And we might need to put them in here. So let's do that right away. Cool. Everything seems to be fine so far, but we haven't done much besides some plumbing. Okay. So we are tracking these things, right? But we are not yet tracking whether they are used or unused. And React will basically be sort of always unused from this perspective. Obviously, we should, once we have proper register allocation, we will make use of it a lot, because if you remember, all of our operations like sum and divide and whatever, they all use arrayx as their temporary register. Some use R10 and some use R11. And right now it all works sort of, just because I was very careful in assigning them, and our test code is not that extensive, but in reality there are already problems in there. Anyhow, and these things, these four registers, their usage will depend on, first of all, whether there is an argument in that position. So if we only have one argument, then these three will not be occupied. And if we do have them, then they might be occupied, depending on whether the argument actually fits. I mean, actually, no, not really. They will always be occupied. So we have this function arg, which have function push argument. Is it part of this things? Yes. Okay, so this is gonna be a bit tricky. Let me think about how to deal with this stuff. So the issue right now is this thing was accepting a function descriptor, and I think we need to change it to accept the builder, or we will need to change how the function deals with its code and attach code block then to the function itself. It is something to think about. So maybe code block should actually be a type of operand instead of a separate thing. But for now, I'm just gonna change this stuff to accept function builder. Builder. And then I'm gonna say function descriptor function star descriptor is builder value descriptor, and cert descriptor function. Something like that. It's called function. Okay. Function push arguments. Okay, we have the builder here. Outer builder. I guess we will put builder into here. Who else needs to do this? This seems a bit of a useless function, because It's never really frozen now. Um, eh, I will get rid of it separately. Get rid of this function. Okay, and this stuff is a bit awkward. Um, hmm, what shall I do about that? So it doesn't have a function builder, so it doesn't really have a code block, but it does have a descriptor. That is a very interesting question. I think for now, I'm going to comment this out and see what is gonna be unhappy, because we might end up just doing this differently. It looks like we don't even have the tests that look for this stuff, so probably for now this is fine to remove and then resurrect in a new form. Okay, something is very unhappy. And the only really change I can think of happened here. Descriptor function. That seems fine to me. Okay, let's just see what's going on. Okay, the problem is builder is null here. Okay. So looks like my refactoring is no good. And we can't really do it that way. Okay, how else can we go about this stuff? So what we could do, yeah, I guess I know what we can do. Since this thing actually returns a value, is anyone actually calling this? No, okay, great. So I actually can remove it. So here's the idea. I'm gonna do it here. So I'm gonna say if arg value type is arg value operand type is operand type register, then I'm going to mark it as such. So I will say builder so if builder, then actually probably better do it that way. If it is not external and it's a register, then we need to save it. So we do register bit set value operand reg, and here's gonna be builder code block register occupied bit set. Good. Let's check if that works. Okay, that is fine. Okay. So what did we do? There isn't really new functionality, but now we actually know which registers are volatile or non-volatile, and we know whether they are occupied or not. And here's where it becomes important, and I think this would be the thing that we will do today. Right now, there is a very straightforward mode of failure that I probably can even create a test for. So let me open this stuff and let's see. Yeah. Let me think about how to best deal with this. Yeah, okay, that will work. Should correctly save volatile registers when calling other functions. So here's what right now shouldn't work, and I think it won't. We have sort of outer function, outer type void to S64. No, that needs to be S64 to S64. So it will have an argument, so it's X S64. It returns S64. That is correct. And what it will do is it will call inner of 42. Doesn't really matter what the value is. Inner is going to be also X. And inner will say X is, I don't know, 21. We can even make it void. And it just returns X. Actually, inner, let's say, let's call it of 0. Or 1, doesn't matter. Okay. So if we call this with 42, we would expect to get 42, right? Because we get this thing, we call the inner function with our arbitrary value. It's just an immediate. It should not affect us in any shape or form. And we just then return our value back. Inside the inner, however, we just take X and we assign it to 21. My conjecture is that if we do this check, it will actually turn out that X is 21. And if that's the case, then we will go look at the assembly, figure out why. Yeah, okay, so as I thought, this test actually fails. So we would say something like U64 expect actual is this. I'm just splitting it up so it's easier to step into the disassembly. There is no really other functionality here. Where is our volatile stuff? Yeah. Okay, so we run this thing. And that's probably the wrong feedable. No, that's the correct one. Did I not rebuild? Can you break here? Okay, it fails for some other reason. And why exactly does that fail? So we have result. Technization is happy with this. So who is unhappy? Okay, that is not what I wanted to do. I wonder if it is this assignment that it doesn't like. Let's see. No. Okay. Yeah, I get what the problem is. There needs to be a line break in here. So actually, let's undo all of that. We say actual. Here we either need to put a semicolon or a line break. Yep. First of all, let's see that it actually does fail. Yes, it does. And now we can make a breakpoint over here and look at the disassembly to see what's going on. So we step inside. And this is where the issue lies. Actually, we don't even need to do anything inside of that function. Yeah. This is the starter function. We are allocating some space on the stack. That's fine. And this is our issue. When we're calling a function, we will need to put the arguments in the right positions, right? So we put 1 into our CX, and this is exactly what we asked our program to do, right? So inner is 1, but we also want to return this parameter back, which was also passed to us inside RCX. And this is why these registers are called volatile or caller saved, because it is our responsibility of the caller to save those registers if we find them interesting or occupied before calling any downstream functions that may mess with them, including the fact that we are putting arguments in them. So this is why this thing will produce result 1 instead of 42 as we expect. So this is what we want to fix now, and we should have all the stuff that we need to do that. So how does that go? We would have call. I don't remember exactly how it does. So this is match call arguments, and this is okay. This is cast, and this is function call. I think this would be then what we want to deal with. Yes, this is the meat of the stuff. Now, how do we do this? I think it is even in the side of overload that we need to do. Yeah, this is probably the right place to do it, because this is where we actually move the arguments in their respective positions. So for now, let's do it here. How do we go this? Well, we say for U64, or actually it's S32, unfortunately, I think. Like this, register. Reg index is 0. Reg index is less or equal to register R15 plus reg index. And then we say if so what we are trying to do is we need to go through the whole list of registers, and we check if that register is volatile and that register is occupied. Then we will push it to the stack before calling. Actually, now I'm wondering, can we actually do that? Because then our stack will end up being misaligned. It is a bit of a pickle. So it looks like we will need to reserve stack space for this and do moves instead of pushes to make sure that the stack keeps being aligned. But regardless, our job is to figure out which of the volatile registers are occupied and save them somewhere. So let's do that. So if register bit set get of builder code block register volatile bit set, and then we say operand, let's put it here, operand star reg operand. Maybe it should have been register index, I don't know. We'll see how it goes. Type is operand type register. And then reg is reg index. That's a build. No. Cascade doesn't need this. Okay, so if this register is one of the volatile registers, now we need to do another thing that says if it is also occupied, then we need to save it somewhere. So value star temp or saved is I already forgot how to get some stack space for us. Stack, reserve stack. Okay, so that's good. We can take that. Reserve stack, the stack builder, and we need to have a descriptor, and descriptor as 64. Good. And now we say move value builder code block instructions saved and we will need to create a value. So value descriptor, maybe it's best to create it here and say value to save is descriptor as 64, and then we have star reg operand. Maybe I should not make it a star here, instead do it like that. And then we can probably even do it like this, so we don't have to copy a bunch of stuff around. Descriptor. Okay, it needs to have source location. Okay, we have that. Cool. Everything should still work as it did before, so it still should have that failing test, but we should not have any new failing tests because we are just reserving some temp space and moving things around. Okay. Move M64 R0. Well, R0 is basically RAX. We cannot. What? I'm very confused. Let's go to here and go to move. That seems to be matching. Wait. RM64. Is it possible that my encoding is actually screwed up? That seems to be totally fine to me. So if we have memory indirect and we have register memory. Okay, right now I'm really confused. But I do know what actually is going on. Because that error 0 is should have given me a thing that it's not the index of the register. This is saying that the size of it is 0. So where I screwed up was that I should have given the byte size here. Byte size is 8. Okay. Cool. So as I said, we still have that failing test because we are just saving without restoring the register. But if we now go and look inside of the assembly, we should see that saving. And here it is. So this is what we would want to see. This is great. Now the only thing that is left is to restore it afterwards. Now, there is another optimization work that needs to be done, which is not happening right now. We reserve stack, but we never release stack. So that means that if our function has, like, I don't know, it calls 20 other functions, that every time we call other functions, we will get new stack allocation, which is sort of unnecessary. Now, when we get to the proper register allocation, that might be solved in slightly different way. We'll still have to release stack, but it will be part of the general allocation strategy, maybe, I don't know. But for now, it's fine because this is more or less just efficiency problem. It has no real, doesn't really affect functionality in any way, at least it shouldn't. Okay, so we save this stuff, but we don't actually restore it. And this is where we would need to, I guess, put this somewhere. How do we do that? So we need to remember in which stack location did we store which register. Okay, so let's create a temporary struct. We say typedef struct saved register value. Just save the register, and then we also need to say typedef dynamic array type. Might be best to actually not make it a dynamic array. But right now I'll do that. It's fine. It's just easier to deal with it that way. And we would have here value saved, value register, I guess we can just save register index, right? So register reg and value star stack location. So we say array saved register saved array. We make the array. And then we can push stuff to it. So dynamic array push of saved array and then saved register it reg is reg index and we can, maybe it's better to put a value here, value star saved. So we say saved is to save and stack. Oops, that was my mouse flying around. And stack, maybe let's call it stack value. That would be understandable. We would say like so. Okay. Now we also know where we save this stuff to. And now we, after all of this is done, so just a bunch of calling code. Return result. Let's unify this into one return, otherwise it will be a bit awkward to deal with this. So we'll say value star result is 0. Why does it move it? Not sure. Okay. Let's check that this still works. Okay, it does. And now back to our stuff. We go through this again, but then actually we don't go through this. We go through e64i0. I mean, I guess we don't need actually that array. Or we do. Yeah, it's fine like as it is. I was just thinking that, yeah, we could figure out how to do it without an extra array, but for now it's fine. Dynamic array links of saved array plus I saved register reg is the array get saved array and then I, and we just do move in opposite direction. Here it's actually very, very simple. So we move it from reg. It's not very reg actually saved, and to reg stack value. And let's add a to-do. Stack allocation. So just a reminder for myself that here we should actually say that that stack allocation is no longer interesting to us. We were only using it for the duration of this stuff. Okay, let's see how it goes. And we have a passing test, which is always great. Let's, as a last thing, take a look at how it looks like inside of assembly. I don't think there's anything particularly crazy there, but now we have the right thing, right? So before we call the function, before we move any of the arguments, we just gonna save our volatile registers to the stack, and then we restore those volatile registers from the stack, and then we do whatever else we need to do. Now, obviously, this is not very efficient. So ideally, if you try to run the same program inside of a proper compiler, I know MSVC, GCC, doesn't matter, then what it will likely do is it will likely save RCX inside of another register instead of saving it inside of on the stack, because it's much faster to put it in another register. I don't know when would be the time when we get to that, because the issue is trying to understand whether you want to save it onto the stack versus onto the register is that you need to know the live regions of each variable, right? You need to know that we will actually use this argument after calling this function. Or yeah, I guess that would be the easiest way to explain it. Because right now our compilation is fully linear, right? We don't really go multiple times over the code, or at least I try not to. And that means I cannot look ahead and say, oh, actually, right in the next instruction, we will need to return it to RX. So probably better would be for us to save it inside of RGX or yeah, maybe RGX or whatever, one of these things, instead of putting it to the stack. Maybe at some point that will happen. But the whole register allocation, it has an optimum solution, but optimal solution often requires quite heavy processing and a bunch of graph theory. If you're interested in that, you can take a look at, just type in register allocation paper and you will get a bunch of computer science papers on how to do that, but it's a gnarly topic, and that's definitely not what I'm looking for anytime soon. I'm interested in correctness. This is why we did this stuff now. We will try to not reuse stack space if we can. Maybe we will switch to actually using registers if they're available. We could like go through the register and say, other unoccupied registers I could shove this to before I move on. So that could be an option. But for now, this is perfectly fine. It fixes our test, so our stuff is now a bit more robust, and this is always good to have. So that would be all today. I think that is some nice progress. We are making our way towards register allocation, and hopefully we'll continue on that or maybe some other topic next time. Thank you very much for watching and see you then.